Okay, good morning to all of you. I hope all of you hear me and see the uh, screen also, isn't it? ಕಾಣಿಸ್ತಾ ಇದೆಯಲ್ಲ? Hello.
Yes, sir.
Okay. So in the last class, we are discussing about the origin of the solar system, and in which we have tried to understand how the Earth might have been formed something 4.5 billion years ago. So now uh, there are many hypotheses about the origin of the solar system, but whatever may be the hypothesis, starting from Big Bang, almost all these hypotheses should be able to explain these five characteristics of the solar system that we observe today. One thing, being the student of science, all of you know, all the planets orbit the sun in the same direction and in the same place. So thus the collision of the planets are avoided because each planet has its own orbit, and within the specified orbit they uh, revolve around the Earth in the same direction and in the same place. And another very interesting thing, if you observe, in the last class only I have told you there are certain planets which are rocky, which are few are more gaseous, what we call Jovian planets. The planets which are closer to the sun are small and rocky, and as a result, because of their small size and rocky nature, they have few moons. Moons means satellites to the respective planets, because as the Earth has one satellite, what we call moon, like that all other planets are also having their own satellites, but the number of such satellites are less to the planets which are close to the sun. Then the planets which are away from the sun, what we call the Jovian planet, they are large and they are more gaseous or icy materials, whereas the one which are very close, they are rocky and small. The one which are far away, they are more gaseous and icy material. And another very interesting thing, even the satellites which revolve orbit their respective planets, they also orbit in the same direction as the planets orbit the Earth. So the direction of the movement of all the satellites are as the are of the same as the planets orbit the sun. And then oldest meteorites that we could collect now is something 4.5 billion years old, and planetary surface of all younger planetary surfaces are all younger than the oldest meteorites, whatever the planets we have studied, because till now our information with respect to the all the planets are not perfect, but whatever the little information that we have gathered about the surface of the other planets also, they are much younger than the oldest meteorites that we have collected. So any of the hypotheses which try to explain the origin of the solar system, it should be able to explain all these characteristics. So then all these planets are affected by the magnetosphere and the solar wind. Hello, this all these planets. This is an example how Earth's magnetosphere and solar wind. Early Earth formation, the solar wind blew the light gases, especially hydrogen and helium, to the further reaches of the solar system. Actually, what has happened initially, when the solar system was formed, it was mainly having hydrogen and helium as the gases. But the solar wind, which uh, originates from the sun, it blew these light gases. Being the student of chemistry, helium and hydrogen are the very light gases. This solar wind has blown this uh, hydrogen and helium gases to the further reaches of the solar system. So as a result, the planets which are in the further reaches of the solar system are having more gaseous mantle rather than what the planets that are closer to the sun has. Now, we have a fairly good idea about the Earth's interior.
ಇವತ್ತು ಗಗನದಾಗೂ ಡೌಟ್ ಕಡ
So,
ಮಳೆ ರಾಶಿ ಕಡಲ್
hello, please mute your microphone. Please, I'm hearing lot of noises. Please, but if you don't hear me, one of you switch on the microphone and tell me if at all any problem and other things. Otherwise, please mute your microphones. The Earth's interior, if you look into this, actually the Earth is made out of four layers. The inner core, which you can see here in the cross section I have shown you, it is more solid. And surrounding this solid core, you can expect a more liquid outer core. Then surrounding that, you can see the solid mantle. And finally on the surface, this what you call the Earth's crust. Um, Earth's crust that you can see. Here, this is the one where you can see the inner core, where the temperature uh, and very high, and above that also the temperature is very high. So because of this is because of the rocky nature. So that's why even if the high temperature it is solid. But whereas here the outer core, where the temperature is in between 3000 to 5000 degree. Sorry, this is about yeah, different variation even up to 3000 degree, and it's at the depth of something 3000 to 5000. It is having more molten or liquid one, and what you call lava sometimes which uh, gas out of the uh, outer core, that comes and forms the what you call this responsible for earthquakes as well as uh, um, many other catastrophes. Then out above that there's a solid, and surface is again solid in nature. So this is another very interesting photograph which will show you the cross section, the inner solid core, outer molten mantle. It is also called as, and this outer margin of the outer core, what we call D layer, extends slightly into the lower mantle, and then surrounding that there's a what you call the final outermost layer, where you can see the mantle. In some reason the mantle will be thick, in some reasons the mantle will be thin, and there is lot, and that's why this particular region which is marked with this black arrow, it is called transitional zone, and it is mainly made up of basaltic magma source. So this is the 3D image of the earth crust. Of course, a 3D image of the earth crust which has been taken in the San Francisco Bay Area uh, by measuring the earthquake waves, and with this three-dimensional figure has been constructed. Of course, this is the East African Rift, uh, where surface expression of a mantle hotspot, which you can expect here, the surface, the mantle hotspot that has been caused, of course. So now, yeah, here you can clearly see the up to this mesosphere, then seismic low velocity zone, and that is known as asthenosphere, and it is partly uh, molten. Above that, you can see the granitic crust, basalt crust, and what you call lithosphere. And above this only, you can see the ocean as well as different continents. So this is the surface. Now, before understanding the formation of this, we are expected to know the different chemical elements in the earth. Especially if you see the present, this is the present distribution of major elements. that's uranium, thorium, helium, argon in the Earth's atmosphere, as well as crust in seawater. See here, in the Earth's atmosphere at present we have nitrogen, oxygen, carbon dioxide, argon, helium, and all those things. But uh, below the continents, you can see even silicon oxide, aluminium, iron, calcium, sodium, potassium, manganese, uranium, thorium. In the ocean also the same elements have been dissolved. In the mantle, if you come to this, the mantle, you can see more heavier elements or minerals like iron, magnesium, calcium, aluminium, there is silicon oxide and all those things. Uh, So now the this is the zircon grain or a crystal that has been got from uh, Canada, and probably the zircons have been dated back to something 4.03 billion years ago. That must have been formed, and by these are all the evidences for us in calculating or determining the age of this Earth. See, this is another one is Ekestragens Great Cell Province in Canada. Oldest dated rock on this is the oldest dated rock on the earth, and the age of this rock is something 4.03 billion years. And and this must have been one of the first crustal rocks to form either at late Hadean or shortly thereafter. Now you may ask what is Hadean. I will come to that later, a little bit later. This is another slide which is showing you the density stratification with regard to the gases. Lightest in the further out, for example, the hydrogen layer, helium layer, even atomic oxygen layer. But uh, you can see the ozone layer. So these are all uh, based on the density stratification. Vertical logarithmic scale it has been, but we need not go to this much detail. So this is evolution of the Earth's atmosphere. I will come to this later. Now, again to summarize what we have discussed, the origin of the solar system and Earth, cloud of gas and space dust, what you call nebula, began to contract something 4.6 billion years ago. This we can mark as the beginning of the origin of the solar system. When the cloud of gas and space dust together what we call the nebula, when it started contracting something 4.6 billion years ago, that marks the beginning of our solar system. Before continuing that, I would like to introduce two more terminologies here. One is asteroids and another one is the comets. What are asteroids? Asteroids are the rocky remnants from our early solar system. Even prior to the formation of the solar system, these asteroids were there. Asteroids are rocky materials. Most asteroids orbit between inner and outer planets now. Sometimes, occasionally, the asteroids um, reach the Earth's surface as meteorites. In ಕನ್ನಡದಲ್ಲಿ meteorites ಏನು ಉಲ್ಕೆ ಅಂತ ಏನು ಹೇಳ್ತಿರಲ್ಲ, ಉಲ್ಕಾಪಾತ ಅಂತ sometimes you read it, and in a dark night, if you observe, sometimes you uh, feel that some star is falling. It is not the star, but it is the meteorites, providing scientists with the information about the formation of inner solar system. These asteroids sometimes, uh, most of the time, they get burned when they come in contact with the Earth's atmosphere. But if they are sufficiently large, sometimes they reach the Earth crust, and that gives us a lot of information about the uh, formation of our inner solar system. So this is one image, and that is known as Galileo orbiter image of an asteroid by name Ida. It has been it's the courtesy of NASA. See, this is one such asteroid which has reached the Earth, and you can see it the rocky one. And the analysis of this gives us the information about the origin of our solar system and the minerals and other materials which were present during that time. Another one is comet. Comets ಅಂದ್ರೆ ಗೊತ್ತಲ್ಲ ಕನ್ನಡದಲ್ಲಿ ಧೂಮಕೇತು ಅಂತ ಹೇಳ್ತಿರಲ್ಲ. Comets are formed in the outer reaches of our solar system in early in its development. These are made out of ice and dust. Uh, Usually, the comets are seen on the periphery of the solar system because very close to the sun, all of you know that there is no ice; it is more solid. So, they are found on the periphery, outer reaches, and they are mostly made out of ice and dust, and these are also derived from the early solar nebula only. And sometimes when they move, comets come close enough to the sun, and once they come close enough to the sun, they get heated up. When they get heated up, they release a long tail of dust and gas. So as a result, they look like broom. Broom ಅಂದ್ರೆ ಗೊತ್ತಾಯ್ತಲ್ಲ, ಕಸಬರಗಿ ಆಗಿ ಕಾಣಿಸ್ತವೆ, with a heat head and a tail. A nucleus of the comet Halley. A few years back, you might have seen. This is how it appeared, because see, this is the head, and here you can see the tail. Uh, this is the comets. Now, just two slides back, I have mentioned one term, that is Hadin. What is this Hadin? Hadin is the name given to the time period in which Earth was formed by accretion and meteorite bombardment. The time period, it's a pretty long time period of few billion years. That time period, or it is also known as eon, eon is the time period. Hadin is the name given to that time period in which Earth is formed by the accretion as well as the meteoritic bombardment. So here actually this geological time scale, what we call the time duration, and the chronologically, if you arrange that in the history of Earth, that has been divided into eon, then into era, then into period, then into epoch, like this. So there are only four eons: Hadin, Archean, Proterozoic, and Phanerozoic. And each Hadin is the oldest one, and the era, only one era, that's Precambrian. Something this ended 543 million years back, and all other eons are the most recent one, where you see different eras: Precambrian, then comes Paleozoic, Mesozoic, Cenozoic. In Mesozoic we have different periods. One is Triassic, Jurassic, Cretaceous. If you come to Cenozoic, we have Paleocene, Eocene, Oligocene, so like that. So this Hadin is the name given to the earliest time period, what we call eon, and it was truly hell on the earth. We should say that the earth was not calm and peace; it was the hell, because there was a constant bombardment of meteorites and outgassing. Come and almost the surface of the earth was in a molten state, and the atmosphere during that period was also reducing one, because there is no oxygen, and uh, the same type of atmosphere even today you see on the Jupiter mostly. Then there were some gases like methane, ammonia, hydrogen, and helium, and some traces of neon has also been recorded. But mostly the important gases which prevailed during that time were methane, ammonia, hydrogen, and helium. So uh, you know, the planets, protoplanets. First, all these planets of the solar system originated from the protoplanets, and all these protoplanets were created by the nebula. And all protoplanets were initially homogeneous because they were more gaseous and larger in size than the today's Earth, because it was more gaseous. But when it started solidifying, the shrinking process continued, and Earth could attain the present day shape and size, lot of volcanic activities, no continents or no oceans at that time. And you can imagine there was no life at all. Life is the most recent one. What has happened when the early Earth was formed? Proto-Earth experienced this density stratification. Probably in the last class I must have told you, heavy something in its density, if the heavier materials, rock materials in the center and low density material like gases on the outside. This is the principle. So even here also you can see the same thing. Here you can see the solid materials, liquid, and mainly the outer surface, that's the gases. So density stratification for the Earth's early atmosphere. Why? Because when the heavier metals like iron oxide, iron, nickel, then magnesium, they started because of the uh, density stratification that sink into the center. When they sink into the center, naturally the water vapor and the carbon dioxide gas which was there, it started outgassing. Something, it is just like if you put a stone in a water, the water will spill out because of the force by which this stone enters. The same thing has happened when it was everything was molten and heavier material started sinking in the center, and naturally the gaseous part which were in the center started outgassing. And actually, this initial atmosphere on the surface of the Earth is the result of this outgassing of mm, the mainly hydrogen and helium. Uh, Initial atmosphere was rich only in hydrogen and helium, but you know the present atmosphere rich in nitrogen and oxygen. This is the later entry. So, if you talk about the first atmosphere which has been formed, the early atmosphere uh, must have been like that of the atmosphere which is prevailing on the sun. Even today we know that the sun's atmosphere is mainly made up of hydrogen and helium. But this atmosphere of hydrogen and helium didn't stay for a longer period of time for practically two reasons. One is the gravity of the Earth. Earth was of the modest size at that time, not of this size, or it was not very large also. It was of the modest size. And what has happened? The gravity has been formed. When the gravity of this modest Earth was not strong enough to prevent such light gases from escaping into the space, because the gravitational force exerted by the Earth was very minimal, so it couldn't prevent these light gases to escape from its gravitational force. So naturally, most of these gases, hydrogen and helium, escaped into the uh, outer space. So that's why we don't see that much amount of hydrogen and helium even today. Uh, Something it appears like around 30 million years after the Earth's formation. At that time, there must have been some bombardment of some large object, maybe of the size of Mars. The As a result of this, also what has happened was a piece got separated, and the moon must have been formed. This is something 30 million years after the formation of the Earth. Actually, in the initial year, when the Earth was formed initially, there was no moon. It was after some bombardment of some a large object. We consider that it may be of the size of a Mars and other things. Piece of Earth got broken, and that has become the moon today. And this bombardment from the atmosphere, that has also helped these light gases, hydrogen and helium, to escape further into the further deep into the outer space. This is uh, how the early atmosphere would have been. So this is the photograph how it would have been when initially it has been formed. So this is the formation of moon from the debris of the collision. When there was a collision, lot of pieces got broken up, and all of them started colliding and merging, and as a result of which we this present day moon must have been formed. So, how was the condition on the earth? It was hell. Literally, the surface of the earth during this period was extremely hot, and numerous lot of volcanic activities were taking place. Because of this, the earth atmosphere was fully hot, and not only that, lot of meteorites used to hit the objects, because at that time there were a lot of meteorites in the atmosphere, and earth was under the constant bombardment, continuous, of the objects of various size. As a result of this, what has happened was uh, uh, life was not possible, but slowly the earth started to cool down. How? Because whatever the heat that has been generated, it dissipated into the outer space. Because of the dissipation of the heat into the outer space, and simultaneously, even the volcanic activities were also slowed down, and number of bombardments the earth used to receive was also minimized. Because of all these things, slowly earth started to cool down. And when the earth started to cool down, the secondary atmosphere began to form. The primary atmosphere, as I have told you, it was only hydrogen and helium, and as you know, most of them escaped into the outer space. Probably this must have been the condition on the earth at that time. So that's why I have told you it is uh, the hell. It is the hell. Certainly not a heaven like the present day earth. So see, there were a lot of volcanic eruptions and all those things. Now, when the earth started cooling down, the earth's second atmosphere started to appear. New atmosphere. How? Thanks to these volcanic activities. The new atmosphere was established because of outgassing of the volcanoes. Uh, the mixture of gases the volcanoes used to ooze out, probably very similar to those of today's volcanoes. We assume, because now also now and then we hear there is some volcanic eruption, and during this period, what has happened? The outgassing of the volcanoes mainly contain water vapors. Not water, but the water vapor. Roughly 80% of the gas which come out of the volcanoes were water vapor. Then another 10% was carbon dioxide. See, remember, secondary atmosphere was having more amount of carbon dioxide, 10%. Actually, the present day carbon dioxide percentage is 0.03% in the atmosphere, but at that time it was 10% carbon dioxide. Then nitrogen few percent, less than 10%, because but now we have around 70%, 70 plus percent of nitrogen. Then along with that, small amount of carbon monoxide, HCl, hydrogen sulfide, sulfur dioxide, methane, ammonia, and other trace gases were also outgassed from these functioning volcanoes at that time. So that's why it's not wrong if I say whatever the Earth's second atmosphere has been formed, it is the contribution of these volcanoes. Because earlier a primary atmosphere has disappeared into the outer space. Now a new atmosphere which has been formed because of the outgassing of these volcanoes. See, this is the photograph which is showing the volcanic eruption, and even today the gas which come out of the volcanoes, it has something 80% water vapor and 10% carbon dioxide and all other materials, as I have discussed. Even in the second atmosphere also, virtually there is no oxygen. No oxygen. no ozone layer. So, in the absence of ozone layer, what happens? Sun's ultraviolet radiation flooded the Earth's surface. So, when there is no check for the ultraviolet rays, all these ultraviolet rays used to hit the Earth directly. And then, because of the outgassing of the volcanoes, huge influx of water vapor into the Earth's atmosphere. 80% was water vapor. And slowly, the water vapor started cooling. And what happens to water vapor starts cooling? Then there will be clouds formation and torrential rainfalls continue because 80% Earth's atmosphere was very rich in terms of uh, water vapor, and because of the cooling they precipitate rain continued. But at the same time, another very interesting thing was at that time sun was about 30% weaker than today. The amount of energy that the earth used to get from the sun was only 70% of what we get today. That was sun was 30% weaker than what it is. Now you may ask, when the sun is 30% weaker, earth should have been frozen or should freeze. But that didn't happen because 10% carbon dioxide, it created the greenhouse effect. Nowadays, all of us talk about the greenhouse effect, which is responsible for rise of the global warming or rise of the temperature. But initially, the same global warming saved the earth from freezing. Otherwise, when the earth was formed and when the second atmosphere was formed, the sun was 30% weaker than what he is today. And this must have uh, made the earth to freeze. But that didn't happen because there was a thick layer of carbon dioxide which functioned as a greenhouse and uh, help to increase the global temperature. Global warming was also the phenomenon at that time, and it prevented the global freezing at that time. Then, in the first 2 billion years of Earth's evolution, the atmosphere acquired a small amount of oxygen. How? Not by photosynthesis as you see today, but it was because of the photolysis of water, that is splitting up of the water molecule by solar radiation. I have told you there is no ozone layer. Directly ultraviolet rays used to hit the earth. So when these ultraviolet rays passed through this water vapors, they must have helped in splitting the water molecule into hydrogen and oxygen. Now, how do we say that this small amount of oxygen was formed in the secondary atmosphere? Because even we can see today some minor rust in some of the early rocks. When there is a rust is nothing but the iron oxide. Iron is already there. Unless there is a oxygen, you cannot expect the rusting process. So even if you see some of the older um, early rocks, on the rocks you can see some minor rusting. That indicates that in the initial atmosphere, because of the splitting up of the water molecule, some amount of oxygen must have been placed, and this must have caused the rusting of the rocks. Then the oxygen also led to the establishment of an ozone layer, O3, and that reduced the impact of ultraviolet radiation on the Earth's surface. Even today, you know the role of ozone layer, and this must have started during that when the early oxygen evolved. Then slowly the rise of photosynthetic bacteria, early plants, oxygen level must have began to rise rapidly, and that is also shown that more and more rust on the rocks we can see that. And it is estimated that the oxygen rose to the present level in between 2.5 billion years ago, 2.5 billion to 500 billion years. In that period, the oxygen uh, uh, rose to this present day scenario. So this is the free oxygen. This is the billion years, and see how the origin of first prokaryotic cells, eukaryotic cells, and as a result, it reached this the present day status. And I was talking about the rusting of the rocks. See, all these red coloration to these rocks are because of the rusting. And when you observe the rusting on the rocks, it indicates that there must have been some few or there must have been some amount of oxygen made available for the formation of iron oxide. Then from secondary atmosphere, slowly the tertiary atmosphere or the third atmosphere evolved. Um, when carbon dioxide was increasing, contrary to that, when the oxygen was increasing, contrary to that, carbon dioxide showed the decline. Why? There are several reasons for decline in the carbon dioxide. One is um, slowly when the carbon was increasing, some photosynthetic bacteria they started utilizing the carbon dioxide for the purpose of what is known as photosynthesis and started producing the organic matter. And many of these organic matters which were formed during those days got lost into the system. Probably they dropped to the bottom of the ocean and got buried. Then chemical weathering was, which helped in removing the carbon dioxide from the atmosphere. Chemical weathering, what has happened? Water and carbon dioxide together it form the carbonic acid. And silicate rocks and carbonic acid give the calcium carbonate, silicon oxide and water, and all of them got settled or buried in the oceanic crust. At first, this chemical weathering happened in the absence of life, but this particular process of chemical weathering was accelerated when the living organisms also came into existence. Later, what has happened? Many of the marine organisms started incorporating these carbonates which are formed, calcium carbonate, are incorporated in their shells naturally because of the heavier uh, weight. They started falling at the bottom when they died. So, as a result, what happens? That much amount of carbon has been taken away from the atmosphere and got buried in the oceanic crust. Initially, all marine organisms were having the shells, and all of you know the shells are made up of calcium carbonate. So, for the formation of calcium carbonate, the atmospheric carbon dioxide was used. First, carbonic acid was formed, and this silicate rocks and carbonic acid together formed calcium carbonate. So, ultimately, because of all these things, whatever the carbon dioxide was there in the atmosphere to the tune of 10%, it was removed from the atmosphere. Then what happened? Simultaneously, Sun was becoming more and more powerful, more stronger, and whatever the heat that is generated to maintain the temperature on the Earth was given by the solar radiation, and the greenhouse effect that has been caused by the carbon dioxide withered slowly. Simultaneously, some more changes also took place. Sulfur compounds, the sulfur dioxide and all, were also taken out of the atmosphere as acid rain. Because you know, sulfur dioxide in the atmosphere comes in contact with water, it forms the sulfuric acid. And slowly they reached the ground and deposited as sulfates. Then the nitrogen gas increases slowly and progressively because it's the inert gas. So the present composition of this atmosphere, where we have more amount of nitrogen, second comes the oxygen, then 0.03% of carbon dioxide. All these present day atmosphere might have been established approximately a billion years ago. 1 billion years. So Earth originated something 4.5 billion years ago, but it could attain this present day form and shape now, that is about a billion years ago. The Here certain problems that we encounter. With lower carbon dioxide levels, the Earth became more susceptible to ice ages. Because I have told you, whatever the global warming that has been noticed even during that time, the carbon dioxide was responsible because uh, secondary atmosphere of the Earth was having 10% carbon dioxide. Um, Here it was susceptible to ice ages. But around 750 to 550 million years ago, the Earth cooled down and became nearly entirely glaciated also, because there was an orbital variation of the Earth was seen. So if you see the Earth history, there are certain period where you see the glaciation. Entire Earth was covered by ice, and when the Earth's solar radiation uh, decreased because of the orbital changes, Earth must have changed the orbit minimum 3 times, uh, and this as a result, the amount of solar radiation received by the Earth was also less, and slowly carbon dioxide level was low. As a result, it resulted in glaciation. If you go through the history of the Earth, minimum 3 times you will see this glaciation. Glaciation is nothing but the entire Earth was covered by um, uh, this ice and snow. Later, with the increase of the uh, carbon dioxide, the global warming started. Again, this ice started melting. Earth was like a snowball at that time. Then you may ask, why did we get unfrozen? Because during that period, even the volcanoes were still putting carbon dioxide into the atmosphere. Though the intensity of volcanic eruptions was less, but still there were considerable number of volcanoes which used to pour carbon dioxide into the atmosphere, and because of the glaciation, what has happened was chemical withering was greatly reduced. Otherwise, carbon dioxide used to dissolve in water and form carbonic acid. But since little liquid water was available, this withering was stopped, and the volcanoes poured more and more amount of carbon dioxide. So carbon dioxide again increased until the greenhouse effect, so that um, large of this earth showed global warming or warmed. And once the warming started, it would have happened very rapidly. It has happened, and again the glaciation period was over, and again Earth was in the present state. In the last 500 million years, if you see, even in the last 500 million years also, climate has not been constant. Warm periods interrupted by ice ages, as I have told you, the glaciation. So much of this variability is because of changing solar radiation due to the periodic changes in the Earth's orbital characteristic. There will be some tilt, and this is known as Milankovitch cycle. Earth's orbital characteristics changes periodically, and as a result, there is a changing in the solar radiation. And but every time when Earth entered into an ice age, immediately putting out of massive carbon dioxide into the atmosphere by volcanoes caused the warming. Temperature on the planet of the Earth, of course, million years before and present day, of course, we need not go to this. So now, okay, we know pretty well about the atmosphere on this planet. But what about the other things? See, they are more gaseous. The atmosphere. These are certain satellite photographs of other planets. But Earth has total how it looks today. This is the atmosphere of the Mars. Okay, these are some of the photographs taken from NASA and all those things. Martin clouds, Jupiter, Saturn, Neptune, both gas giants, Uranus and Neptune. So uh, now with this, I have tried to explain you the origin of the Earth and the formation of the present day climate on the Earth. Uh, So this is the very basic of evolution. Unless we understand the Earth and its atmosphere, we will not be able to understand about the origin of life and its evolution. Can you hear me? Hello? Hello, ಕೇಳ್ತಾ ಇದೆಯಾ?
Yes, sir.
Slide is, you are also seeing the slides. Okay? So now, do you have any doubt or any problem and other things? We can certainly discuss about that. Hello? Now you can unmute your microphone, even video also if you any doubt. Have you understood what I have told? Hello? Hello?
Hello, sir.
Can you hear what I am telling?
Yes,
ಕೇಳ್ತಾ
sir.
ಇದೆಯಾ? Hello?
Yes, sir.
Any doubt or anything, if you have, please feel free. Or if you want any other information or anything. Uh, yes, ಹೇಳಿ. You can chat, you can talk to me. Hello? The ಏನಾದರೂ ಡೌಟ್ ಇದೆಯಾ? ಸೊ ಇದ್ರ ಬಗ್ಗೆ ಐ ಹ್ಯಾವ್ ಎ ರೈಟ್ ಅಪ್ ಹೇಗೆ ಕಳಿಸೋದು ನಿಮಗೆ ಹೇಳಿ. ಹಲೋ ಹಲೋ
Hello, sir.
ಈಗ ಇದ್ರ ಬಗ್ಗೆ ನನ್ನ ಹತ್ರ ರೈಟ್ ಅಪ್ ಇದ್ದದ್ದನ್ನ ನಿಮ್ಗೆ ಹೇಗೆ ಕಳಿಸ್ಬೇಕು ಹೇಳಿ.
Sir, WhatsApp ಅಲ್ಲಿ ಕಳಿಸಿ.
ವಾಟ್ಸಪ್ ನಲ್ಲಿ ಸ್ಕ್ಯಾನ್ ಮಾಡಿ ಕಳಿಸಿದ್ರೆ ಸಾಕಾ?
ಹಾ, sir.
ಸೊ so okay, then probably today evening I will send the recording of this also, and